In this video, we're going to continue going over marginal cost and marginal revenue, but combine it with the idea of local linear approximation. So this is the sequel to part 1, where in part 1 we went over the theory of local linear approximation, or the idea of it rather, and here we're actually going to apply it. So let's suppose that C represents the cost of some business, okay? And this 15 here is just the number of items that you want to produce. So in order for this business to produce 15 items, it'll cost them $2,300. And let's say you furthermore know the marginal at 15. The marginal cost is going to be $108. So this is what's known and given to you. And the question is, can you know another value? For example, how much producing 16 items will be. So remember how this works. You have the value at a particular function. You have the value of the function at a particular point at q equals 15. And you also know the derivative there. So you should be able to get a reasonable approximation for the cost at 16, because 16 is pretty close to 15. So let's do it like this. We have, remember, we use the tangent line, which in this case would be y minus c of 15, and that's equal to the slope times x minus 15. Okay, this is the equation of the tangent line. But it's the tangent line at a particular point, 15 comma 2,300. Okay? And remember, this y value, okay, these y values represents the y values on this tangent line. And we're going to use the tangent line to approximate the value of the function. So how's this going to work? Well, we know this, just use a different color here, is 2,300. This here is 108. And now we want to approximate c of 16. So x is going to be 16. Well, what is that? We're then going to get y equals 2,300 plus 108 times 16 minus 15. But 16 minus 15 is just 1, so 2,300 plus 108 is just 2,408. Okay? And this is an approximation for c of 16. Why is it an approximation? Because we're using information at x equals 15 to get information about x equals 16. That's one thing. And the way we're getting that information is by assuming that the function progresses like a line. Okay? So that's the tangent. That's where the tangent line comes in. All right. So now this is part A. Let's do part B. So we want to approximate 16.5 now. All right? How's it going to go? Again, we're going to use a linear approximation to the function c, and all we know is the marginal at 15 and the actual value at 15. Okay, so how much does it cost to produce 16.5 items, for example? So we have y, so this is for part B now, 2,300 still. That's equal to 108. But now our x value is 16. Let me use a different color. 0.5 minus 15. Okay? But now this is just 1.5. Well, what's 1.5 plus 108 times 108? That's going to be 108 plus 59. So that's going to be 167. If I add 2,300 to both sides, that's going to be my approximation for 16.5. Okay? And what is that value? It's 2,400. 2,467. Okay. And so this is how it would work out in a particular example. Remember, we use the tangent line. That's why we have these equations here. We use the tangent line to approximate the original function. In this case, we don't know if it's linear or not. So we don't know if we're getting exactly these values, 2,408 and 2,467. So that's why it's an approximation. But again, we're just using the line to approximate the value of the function, as long as you know a value of the function at some point and the marginal there. Now, of course, there's a simpler way to do this, and the simpler way is simply by understanding what it means to be marginal cost. If your marginal at 15 is $108, that means that the cost of producing one more after 15, that's the 16th item, producing the 16th item will cost you $108. So the cost of producing 16 will be the cost of producing 15 plus the marginal. And that's what we got. It's just 2,300 plus the marginal, 108. And similarly, if you wanted to do it for 17, you'd multiply the marginal by 2. And so as long as you understand what it means to be a marginal cost, you can also do these problems pretty easily. But again, with the idea of local linear approximations, you have to know the slope of that tangent line, which is the derivative, and a point on that line.